Once again, welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We were discussing unit 6 thermodynamics, and in this video we will discuss about thermochemical equations and Hess's law of constant heat summation. First come to thermochemical equation. A balanced chemical equation together with the value of its enthalpy of reaction is called a thermochemical equation. We specify the physical state along with allotropic state of the substance in an equation because as we change the physical state and allotropic state, the enthalpy of reaction is also changed. Take one example. This is C2H5, that is ethanol in liquid state, plus 3O2 in gaseous state, 2CO2 in gaseous state, plus 3H2O in liquid state. This is a balanced chemical equation. Okay, and along with it, we write the standard enthalpy of reaction. This is equal to minus 1367 kilojoule per mole. Then we can say this whole from this to this refer as a thermochemical equation. Okay. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. Again, this we know, we already discussed. Delta H is negative for exothermic reaction and delta H is positive for endothermic reaction. Remember the following conventions regarding thermochemical equations. First one is the coefficients, that is stoichiometric coefficients in a balanced thermochemical equation refer to the number of moles, never molecules, of reactants and products involved in the reaction. The numerical value of standard enthalpy of reaction refers to the number of moles of substances specified by an equation. Standard enthalpy change will have units as kilojoule per mole. The unit for standard enthalpy of reaction is kilojoule per mole, and which means per mole of reaction. Remember it, per mole of reaction. Once we balance the chemical equation in a particular way, this defines the mole of reaction. We will try to understand with the help of one example. See, this is Fe2O3 in solid state. When react with hydrogen in gaseous state, this will convert into Fe plus water. Okay, and in this reaction, if we want to find out the standard enthalpy of reaction, then we must know the enthalpies of formation of reactants and products, and these are given. Standard enthalpy of formation of water in liquid state is this, minus 285.83 kilojoule per mole. Standard enthalpy of formation of Fe2O3 in solid state is minus 824.2 kilojoule per mole, and standard enthalpy of formation of iron in solid state is 0, and standard enthalpy of formation of H2 in gaseous state 0 as per convention. Remember it, in elemental state, for each element, standard enthalpy of formation is taken as 0 by convention. Now, to calculate the standard enthalpy of reaction, we use this formula. Standard enthalpy of reaction is sum of the standard enthalpy of formation of products minus sum of the standard enthalpy of formation of reactants. And each term is multiplied by stoichiometric coefficient, that is A1. This is the stoichiometric coefficient of product, and this is AI, and this is BI, stoichiometric coefficient of reactants. Okay, now put the values. This is standard enthalpy of reaction. We are mentioning is as a 1. Okay, and this is 3 into standard enthalpy of formation of water plus 2 into standard enthalpy of formation of iron minus, now in square bracket put 1 into standard enthalpy of formation of Fe2O3 plus 3 into standard enthalpy of formation of H2. Now put the values. This is 3 into, this is the standard enthalpy of formation of water plus this is standard enthalpy of formation of iron is 0. When this 0 is multiplied by 2, we will get 0. Okay, this is minus. Now this is 1. What is this 1? 1 is the stoichiometric coefficient of Fe2O3. multiplied by standard enthalpy of formation of Fe2O3, and again this in this term standard enthalpy of formation of hydrogen is 0. When this 0 is multiplied by 3, we will get 0. And if we solve it, we will get minus 33.3 kilojoule per mole. This is the standard enthalpy of reaction for this equation. Okay. Now, if this equation is a divide by 2, okay, that is, we can say each stoichiometric coefficient is multiplied by half. You can say multiplied by half. Then we will get this equation. Half of Fe2O3 solid plus 3 by 2 H2 gas converting into Fe plus 3 by 2 H2O. Then this amount of reaction would be 1 mole of reaction. Okay. And standard enthalpy of reaction would be for this reaction. Okay. Now we are mentioning it as a 2. Apply the same formula. Sum of the standard enthalpy of formation of products minus sum of the standard enthalpy of formation of reactant, and if we put the values, okay, and if we solve it, we will get this minus 16.6 kilojoule per mole. And if this is compared with the standard enthalpy of formation 1, which we discussed previous, okay, then this is the half of that one. But there is no change in the unit. Okay, unit is kilojoule per mole. Okay. Now it shows that enthalpy is an extensive property. It means depends on the amount of matter. Clear? When a chemical equation is reversed, the value of standard enthalpy of reaction is reversed in sign. Okay. For example, N2 gas plus 3 H2 gas converting into 2 NH3 gas, and for this the standard enthalpy of reaction is minus 91.8 kilojoule per mole. If we reverse the equation, that is, this reaction represents the formation of ammonia. Okay. Now see decomposition of ammonia. 2 NH3 gas converting into N2 gas plus 3 H2 gas. Then what about its enthalpy, standard enthalpy of reaction? Magnitude remains the same. Okay, but only sign is reversed. That's why this is plus 91.8 kilojoule per mole. Okay. Now next is Hess's law of constant heat summation. We know enthalpy is a state function, that is depends on the initial and final state. Enthalpy change for a reaction is the same whether it occurs in one step or in a series of steps. Now, on that basis, we can give the statement for this Hess's law of constant heat summation. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Take one hypothetical example. This A is converting into B, and for this the enthalpy of reaction is this. Okay, A can also be converted into B in another way. You can see first A is converting into C, and for this step the standard enthalpy of reaction is, or simply we say enthalpy of reaction is this delta R H1. Then C will convert into D. For this, the enthalpy of reaction is delta R H2, and this is D finally convert into B, and for this enthalpy change is delta R H3. Then according to this Hess's law of constant heat summation, we can say this enthalpy of reaction is sum of the enthalpy of reaction, that is H1, enthalpy of reaction H2, enthalpy of reaction is H3. That is, we will add the enthalpy of each step, and this will be equal to enthalpy change for this step. Okay. Now take one more example. This is the formation of carbon dioxide by reaction of carbon in graphite allotropic form in solid state. When react with the O2, this will convert into CO2, and for this the standard enthalpy of reaction is this minus 393.5 kilojoule per mole. Okay, and when this carbon monoxide also react with the oxygen, then this will convert into CO2. And for this, the standard enthalpy of reaction is this, minus 283.0 kilojoule per mole. By using these two equations, we can find out the standard enthalpy of reaction for this equation. C graphite with solid state plus half O2 gas converting into CO gas. Okay, this change you can also write like this, that is C plus O2. Okay, and this is converting into CO2. This CO2 we can also get if this C react with the half of the O2, then this will convert into CO. And when this CO react again with half of the O2, this will convert into CO2. Suppose this is for our standard enthalpy of reaction, overall standard enthalpy of reaction. Okay, now this reaction is carried out in these two steps, then we can say this is the standard enthalpy of this step. Okay, and for this the standard enthalpy of reaction can be written. Okay, this is 2. Then according to the Hess's law of constant heat summation, we can write this is delta RH, and this is equal to this is delta R, this is H1 standard, okay, plus this is delta R H2 standard. Okay, and we have to find out this delta R H1. Then we can say this delta R H1 standard, this is equal to delta R H standard minus this is delta R H2 standard. Clear? Put the value for the, this is delta R H standard, this is minus 393.5, okay, and this is minus delta R H2, this is minus 283.0, and if you solve it, we will get minus 110.5 kilojoule per mole. Okay, that is by applying Hess's law of constant heat summation, we can find out the enthalpy of standard enthalpy of formation of carbon monoxide. Okay, we can also use this another way, that is reverse the equation second. This when second equation is reversed, we will get CO2 gas converting into CO plus half O2. When equation is reversed, then its enthalpy will also reverse in sign. Magnitude will remain the same, but only we will change the sign. Now if we add the equation, this is equation 1 and this is the equation 3. If we add, then we will get the desired equation, that is standard enthalpy of formation of carbon monoxide. We will get this equation. Then add the standard enthalpy of this also, 1 and 3rd. Also add the standard enthalpies of equation 1st and 3rd. Then again we will get the same result, minus 110.5 kilojoule per mole. In this way, this Hess's law of constant heat summation is useful to calculate the standard enthalpy of reaction or standard enthalpy of formation for those reactions that is direct measurement is not possible. Okay, thank you. Subscribe my channel to get the new videos from this chapter.